This.
Welcome everybody to the first session of this year of the Chilean Probability Seminar. We are happy to have with us someone without whom we would not be here, at least two of us, I think. So it's a really great pleasure to me to start the year with Sylvie Méleard from École Polytechnique that has opened the way of probability many people here.
Thank you, Aurelio. Thank you very much. I'm really very happy to be here. And so Aurelio asked me when I arrived just a few days ago to give a talk. So, I will present you the work in progress we have with Jaime and Pierre Collet from École Polytechnique. So it's not totally finished since I am here to how to finish this work, but I would like to explain to you what we are doing now. So I have to do that. Okay. So the main question we have, with the model we consider is a birth and death diffusion process. That means we consider a measure value process which has a jump, so it will belong to the forward space with values in a set of finite measure on R. And so for any t, it's in fact a point measure. And so that we write like that t is the sum over all individual alive at time t of some Dirac measure on a real number, which will be what we usually call a trait or the position of the individual. So the trait refers to a biological setting where we characterize individuals by some phenotypic or genetic information, which is summarized by a number. Think of, for example, the size at the birth or the weight or something like that. And so I denote by nt the total number of individuals at time t. And so now I describe the dynamics. So I assume that for any individual, so it will always be characterized by some quantity x, some trait x, and it will give birth at trait b of x to a single of x. That's why it's a birth and death. And the descendant will inherit of the trait of its parent. Okay? And the individual can also die with rate d of x. Okay? So we have a function v of x, which is b of x minus d of x, and which describes the growth rate of the subpopulation of individuals with trait x. And between the jumps, that means during the individual life, the trait will evolve, the trait has a dynamics, and it follows a Markov process xt. Okay, that and I call by L. I denote by L the infinitesimal generator of X. So I will show you different examples, but the main framework we have, we will, as I will say later, we will begin so by one individual with trait X, for example, and so here we have time on the horizontal axis. Here it's X on R. And and we have an evolution of the trait of this first individual, and then at some point, this rate b of x, it gives birth, so it gives birth to another individual, which will evolve. So we will see an example of continuous dynamics, but we will also consider dynamics regions. And then this one can die, and this one can evolve and so on. Okay, so that's my process at T. And now I will give you immediately the assumption we consider on this framework. So as I said, we will always consider one individual at time 0 with trait X. And so concerning, the assumptions at 0 concerns the growth rate. And so we assume that the birth rate is bounded. And so by a certain number B star. And that means we assume that D has a linear decay at infinity. Okay, so D of x will tend to infinity. So that means that V, the growth rate, will be bounded from above and will tend to minus infinity at infinity. Okay. And the second assumption we have, so since D is unbounded, we need to make some technical things. We'll see in the proof that we have to cut off this growth rate, and to allow such sort of cut-off techniques, we assume that if we consider the first time for which we fix M, and we consider the first time at which the support of the process Zt goes out minus M. And so we assume that the sequence of stopping times will tend to infinity when M tends to infinity. Okay. So, so it is very well known in this framework that we can associate a non-Markovian semigroup to this dynamics. So we have this process which is Zt, which is a measure-valued process. And so we can consider we could say the linear projection of this measure. So we consider continuous or unbounded. It's enough to consider measurable and bounded function f. And we consider the expectation, so issued from one individual restraint x, so that 0 is delta x, of the integral of f of y with respect to the measure zt. Okay, and so we will often use this duality notation. So I will consider these two notation. And what is important that using Ito's formula, we can prove that this quantity expressed under this form, we have the expectation now, we are at the R-valued process level, so the expectation will be issued from x, and we consider the exponential of integral from 0 to t of v, the growth rate of x s ds, f of xt, where x is the underlying Markov process. So the xt is the process which describes the dynamics between the chunks. Okay, and so we have this relation between the first moment of this process, this linear projection of the measure zt, and non-Markovian semigroup that we always call Feynman Kac semigroup, which is this quantity. And so the growth rate plays a main role, since that gives the weight here in this expectation. Okay. And so, of course, the generator of, if you consider the generator of this semigroup Pt, we have an additional term, which is a term of order 0, v times f. Okay. And so we will have assumption on this semigroup. We will assume that essentially we have a spectral gap property. So we assume that we have a first, say, eigenfunction, theta 0, which will be in C0, tending to 0 at infinity, and some real value lambda 0, such that pt of theta 0 for any t is exponential minus lambda 0 t times theta 0. And furthermore, we assume that we have a spectral gap in the sense that there is another quantity lambda 1 larger than lambda 0, and here a finite positive measure mu 0 that we normalize such a way theta 0 mu 0 as a total mass 1. And such that if we consider the projection pi, the projection operator pi on theta 0 defined by this quantity, then when you consider exponential to lambda 0 t pt minus pi, so in a total variation norm of, if we project on the bounded function f, we consider this quantity that will be bounded by the norm of f in CB here, and time exponential to minus lambda 1 minus lambda 0. That means we have an exponential control here of this estimate. Okay? And so it's well known that the value, so if we consider the spectral property, we are used to write minus lambda 0. If you live in the world of branching processes, it's usual to consider the value minus lambda 0, and minus lambda 0 will characterize the criticality of the process. So if minus lambda 0 is positive, then the process is called a supercritical branching process. If lambda 0 is critical, and minus lambda 0 is negative, then it's subcritical branching process. And our interest will be in, so it was motivated by an example that I will give at the end of the talk, and which was the critical case where lambda 0 is equal to 0. So in the branching framework, I suppose you know, we have it is supercritical. We know that it goes to that it explodes at some point. So if it is subcritical, it goes to extinction, and for critical values, it's more goes also to extinction, but it's more difficult to obtain the results. Okay. And so we will see that we also, for the result I will present you, we also need some set of assumptions. We could say it's related to irreducibility. And so we will assume that PT, and I will explain where this assumption appears, that PT is strongly continuous in C0 and irreducible. In this sense, it means that there exists some time T0, such that for any positive function f in C0 and any positive measure, the integral of PT0 f being mu is positive. And so we will assume that PT maps CB to C0, and also that integral from 0 to t of PSDS map B to CB. So this assumption could seem very technical, but in fact, I will show you in example, but we wanted to obtain standard diffusion processes, but also diffusion with jumps, and also a Markov process with pure, almost pure jump Markov process, and so we needed to have such a
So T0 does not depend on F and mu.
Sorry?
T0 does not depend on F and the mesh.
No, on the
it is for
positivity, no.
Okay. And this stupid question, what is B?
B is a bounded measurable function.
Okay, so bounded to continuous and continuous to
Ouais. So in most of it's a large number of examples, you map immediately from B to C0, but it's a pure, almost pure jump situation. You don't have this. So I show you now, since this assumption can be a very abstract, I show you 3 different classes of assumption where these assumptions are satisfied, and you'll see that I think that make a lot of examples in which how assumptions are satisfied. So the first one is as follows. So here we have really a continuous diffusion process. So the underlying Markov process is a drift Brownian motion, dBt minus some drift term A of xt dt. So we can add some diffusion coefficient here by a change of function, but so say at this level. And so what we assume here that A has at most a linear growth, that the integral of A has at most a linear growth at infinity, and that A prime minus A square is bounded from above. Okay. And so of course the generator of X is given here, and you can see immediately that the process is not coming down rapidly from infinity because of this assumption. And then to obtain this sort of compacity properties, we need to play between the diffusion effect and the death effect. Remember that the death rate is large when X goes to infinity. Okay, so where if you go in if the process go in regions with large X, then you kill a lot the trajectory, okay, because the death rate will be large. And so that by using some Girsanov transformation that we developed already with Servet and Raime with Patrick Catio a long time ago, we can write this, in this case, the Feynman Kac semigroup. So we make a transformation, a Girsanov transformation to go from X to B. And so writing V tilde equal V plus 1/2 of A prime minus S square, sorry, A being the drifter. Then you can write PTF as the exponential of L of X times a new semigroup P tilde T taken in exponential to minus LF. And where P tilde here is related to the Schrödinger operator, okay? And so this operator is well known, and we have the good assumption on V tilde, and we know in this case that we have a discrete spectrum of simple eigenvalues in L2 of dx, okay? And so we have the sequence of eigenvalues which decrease until minus infinity, and we have also eigenfunction here, psi k, in L2 of dx, and we know that they have an exponential d. Okay. So now from this obtained on this semigroup, we obtain information for our Feynman Kac semigroup, and what appears because of this exponential to minus L, since here the good space for the Schrödinger operator is L2 of dx. But if we make this change of function, the good space is L2 with respect to this measure rho, which is exponential minus 2L dy, okay? And so we prove that the function theta k, which is psi k, the eigenfunction for the Schrödinger problem, times exponential to the L. So theta k is an orthonormal basis in L2 of this new reference measure 0. And theta k is an eigenvector of Pt with eigenvalue exponential to minus lambda kt. Okay? And we also prove that theta 0, we also obtain that theta 0 is positive and belongs to C0. It tends to 0 at infinity. Okay? And so we also obtain the spectral gap property with the measure mu0, which is theta 0 times rho. And so that gives us exactly the assumption we needed. And from these studies, we also obtained that Pt is strongly continuous in C0, irreducible in C0, and maps B to C0. Okay, so this case is the simplest one, and it's essentially known. So now we consider a second case which is the first one. So here I write the generator of the semigroup, the Feynman Kac semigroup. So we have the same diffusion generator here, but we have a jump term. Okay. So we have a jump from some x to y with a jump measure k of x dy. And so we assume that this measure is weakly continuous. And we have a technical four-moment assumption here on the jump measure, which is necessary to prove that the stopping times Tm tends to infinity, okay, to control how the process is. And so here we have the previous generator, we studied just previously, plus this new jump term. But we can prove that L1, this jump term, is a bounded operator in C0. And by using some result in Palsy in particular, we can prove that the semigroup associated to this generator, so that now the Feynman Kac semigroup that I call now Qt, which is associated to L, is strongly continuous and compact in C0 as bounded perturbation of the compact operator Pt. And moreover, we have another way to write LF. I can write it as the same diffusion operator, plus V minus the term of order 0 in the jump term, okay? V minus the total mass of K times F, plus another operator, integral of Fyk of x dy, and that I denote by L2. And so here I introduce ST this semigroup. So in fact here it's a semigroup. It's this part of the generator is very close to the generator we studied previously, because we have just changed V in V minus the total mass of K, has the same properties. And we can write the complete Feynman Kac semigroup as STF plus this quantity. So that's well known, it's called the Duhamel's formula. Of course, we have to justify this decomposition, but QTF equal to STF, the semigroup associated to this center, plus this quantity. LQ is a reminder term, okay? And so since we have seen earlier that the semigroup associated with this generator is irreducible in a certain sense, since we have proved, I don't write a second time all the theory, but so we have a spectrum with tilde associated with this semigroup ST, and we know that when t tends to infinity, the exponential to this lambda 0 t tilde t times this new semigroup STF 0 t is a certain positive quantity. And from that, we can deduce the irreducibility for Qt. And then by using this result, we know now that Qt is compact and irreducible in C0. And so we use a result which that we appeared in a book. So Pierre found this book. It's a book by several authors, Arendt and different other authors, which is totally concentrated on positive semigroups. And so they prove that if this a positive semigroup Qt is irreducible and compact, then you have a sort of spectral gap property in C0. Okay? And then we can generalize to CB by approximation and dominated convergence. And to prove that Qt maps B to C0, which is true, we have to condition by the time of the first jumps and to study different cases before the first jump, so then the first jump, and we can prove this property. Okay. And the last example I wanted to show you is a case which has been in particular studied by Bertrand Cloez and Pierre Gabriel. It's a very beautiful paper in the CRAS, l'Académie des Sciences. And they consider a general framework, but they apply this framework to this example, where the underlying diffusion process here is just a drift term plus a jump term. Okay. Here they consider only the f prime, but we can also add some a of x in front of f prime if we assume that a is strictly positive. Or it's never a concept at least. And so of course that gives like that you cannot hope enough regularity to obtain and to obtain particular irreducibility, but they have a sort of ergodicity assumption. They assume that there exists epsilon and k0, such that for any x, the jump measure is larger than k0, an indicator of x minus epsilon, x plus epsilon of y. That means that you will visit this set of okay, with the jet measure. You can go everywhere around X, okay? And why they prove that the spectral property H2 in their paper. Okay. They prove the existence of the function theta 0, the spectral gap, and so on. And so what we did in this example, we proved the assumption H3, that means the irreducibility and the different mapping, and always with the same technique, conditioning with the time of the first jump and studying what happens before the first jump and after. And in the third case I presented here, we can prove that the sequence Tn tends to infinity. Okay. So now I can explain you the results. So the first result we can have without doing anything except to interpret in terms of branching the assumption we have. Is that first we can see that for any initial condition X, the exponential of the expectation of the total mass of the process issued from one individual with trait X behaves in long time as exponential to minus lambda 0 t. We use that, of course. And we also have that if we consider the first moment of ZTF, the exponential to lambda 0 t times the expectation of ZTF, so the first moment of ZTF, when t tends to infinity, will be theta 0 of x, the integral of f with respect to the famous measure mu0 introduced in the spectral assumption. Okay? And in particular, you have the convergence of the ratio. And you see that the ratio will converge, you just apply that, to this quantity, integral of f of 1, with respect to this probability measure, mu0 over its mass. But so it's a sort of quasi-stationary measure for PT, but you see here that you don't divide by the survival probability of the process at time t, you divide by the total mass. Okay? So that's the direct consequences of the assumption. And now our aim is first to obtain so in fact, so yes, we have seen we have already seen some properties of in the long time behavior of the random variable zt of x, but what we want is to obtain asymptotic properties at the level of the process zt, which is a measure valued process. Okay, and so we will consider the behavior of this process conditioned on non-extinction, and we will obtain some quasi-stationary result, but at the level of the measure. Okay, the measure valued process. So that's questions which are open since a long time, and already with Pierre Servet and Raimé a long time ago, we tried to understand such sort of asymptotic behavior. So the strategy we have developed consists in first studying the asymptotic behavior of the moment, all the moments of ZTF. And you will see that we will use recursive equations. And so for that, we essentially use the H0, H1, H2. And second, we have to study the asymptotic behavior of the survival probability. That was the typical part of the work. And for that, we need this additional irreducibilities and so on properties. Okay. So I am just to mention that so we have unbounded domains with unbounded stress, so that's not so easy, and that the underlying diffusion does not come from infinity, but the branching mechanism in another sense, another way, is very simple. So we have just birth and death. So, so as I said here, we play between the diffusion effects and the death effect. That's what gives us all these compactness properties. So it's different of essentially all the papers we know, which consider branching diffusion processes. And usually the branching rate is bounded, but the branching mechanism is really more general, okay? And so I think that the first paper which studies the long-time behavior of such process is in Herring in 77. And but the assumption is really stronger than us. And the more recent papers, there is a large series of recent papers by a group, say a group around Harris, Ciprianou, and Horton. And but there is also Gonzalez, Monet, Wang. So they study sort of framework, but with a more general branching mechanism, with an approach also an approach based on spectral properties and spinal processes that we don't use here. And but their assumptions are not satisfied by our example. In fact, we don't know exactly when they are satisfied. Okay. So now first I give you just an exercise, just a priori bounds on the moment of ZTF. So the first remark is that since the birth rate is bounded, so if you can make a coupling between our process and a Yule process where you have no death and where you replace the birth rate B of X by B star, the bound. And B star is the upper bound of B. And so you can introduce the Yule process, which is just the parameter, the birth parameter B star. And we know that we didn't find this result, but for a Yule process, one can prove that the moment of order n is less than n factorial exponential to n B star t. And for example, to do so, what is well known is that n star t, the Yule process, has a geometric law with parameter exponential to minus B star t. That's a standard exercise. And so, of course, the moment of order n is given by this quantity. And there is a famous identity called Calvez identity relying this value to this decomposition in terms of Eulerian numbers. And one knows that the sum of the first n Eulerian numbers is equal to n factorial, and that gives us immediately the result. And so we see this quantity appearing here, and so that we have already a first control estimate of the moment of ZTF to the order of the moment of order n uniformly in time. Okay, of course on a finite time interval. Okay, so now we will, as I said, we will need to obtain some equation. Some recursive equation between all the moments of the process. And so the problem is that, so usually to do so, we consider the Laplace functional of the measure value process Zt. But if we consider directly the Laplace transform, we obtain a recursive equation involving B and D. And D for us is unbounded. So we want to obtain a recursive equation which only involves the birth rate B. And to do that, we instead of considering the Laplace transform of Zt, we consider the expectation, it's always issued from one individual with rate x, of 1 minus exponential, so W ZTF. So here f is a bounded function and W is a complex number. And to give a sense to this quantity, we assume that W belongs to this okay, justified, but just the control we have obtained in the previous slide. Okay, and so we can prove that this function is analytic in W, and that it satisfies this equation. So to obtain such sort of equation, there is that is very well explained in the book branching. Branching diffusion processes, a book by Zenguli, which is appeared in Springer, I don't remember when. But you condition the expectation always to the first jumps. It can be either a birth or a death, or nothing happened. And if you condition and you explain, you use Markov property. I forgot to mention that ZT here is a Markov process. Then you obtain such sort of recursive equation. And here you see that it only involves the birth rate. Okay. So to do that, since D is unbounded, the first step is to consider to couple the process Z with the process Zm, which is exactly similar, but we replace D by a cutoff, the cutoff death rate Dm, which is defined. Okay, we bound the cutoff, and so we derive the equation for Hm very easily, and then we make m tends to infinity. And to make m tends to infinity, we need to have this assumption that Tm tends to infinity at infinity. Okay, that's the place where this assumption plays a role. Okay, so now since we remember the definition of H, now we can imagine that if we derive with respect to W, it's analytic in W, we will obtain the successive moments, okay, from this quantity. And so that's what we do. So we always do that on the process Hm, and then we make m tends to infinity. And finally, what we obtain is that if we denote by u n f of tx the moment of order n of ZTF issued from one individual with rate x, we obtain this recursive equation on the moment. Okay. And secondly, that's already written here. Now, if we make f is equal to say 1, and if we make w here tending to minus infinity, we can obtain the survival probability. And so if I introduce now u0 of tx, which is the survival probability of the process at time t. Remember, nt is the total mass of the process, the total number of individuals. Then we have also a recursive equation for u0, but here it involves the first order moment. That means the expectation of the total mass here, u1 and 1 of tx, minus the similar term as before. Okay? So we have an equation for the moments, and a recursive equation for the moments, and a recursive equation for the survival probability involving the first moment. Okay? So now, as I said, we consider from now on, we will consider the critical case. We have other results, but very technical, so I think it's enough here. And so first, what we can prove, so we can by the spectral gap property, so the assumption H2, we can prove that U1F is bounded if F is bounded. And by using the recursive equation, then we can prove that the moment of order n of the TF is less than the upper bound of the infinite norm of f to the n times the first moment, the moment of order n of the total mass. That's clear, obvious. And then this the first moment, the moment of order n of the total mass is bounded by n factorial, certain constant d, some constant larger than 1 to the 2n minus 1, t plus 1 to the n minus 1. Okay? And this quantity arrives from this recursive equation. Okay? Well, because we integrate successively. Okay? So we have this t plus 1 to the n minus 1. And so we, moreover, always by a recursive, using first the spectral gap property and then using the induction, we can prove that this moment of order n divided by t plus 1 to the n minus 1 minus, so theta 0 of x, the first eigenfunction, n factorial, the moment of order n of nu, the quasi-stationary distribution x, times a constant, which is the total mass of mu 0 to the n, and b to the n minus 1, and b is the integral of theta 0 squared b with respect to mu 0. So that, remember, mu 0, beta 0, and that's what is given by the spectral assumption. Okay. And we can prove that this quantity converges to this number at this velocity, 1 over t plus 1. So for n is equal to 1, so of course this term disappears, and so you have only a here, and so what we can observe is exactly the spectral gap property. So since theta 0 is 0, so we know that lambda 1 is, lambda 0 is 0, we know that lambda 1 is strictly positive. And in the spectral gap property, we have here exponential to minus lambda 1t, so it's less than 1 over t, for example. And then by induction, so the induction, it's important to have this term for the induction. Okay. And we obtain this property for any n. Okay. So now the difficult part is to study the survival probability. And so what we obtain, as already gives the result, is that if we consider the survival probability at time t times 1 plus t, we prove that it converges when t tends to infinity to theta 0x over b. Remember, b is this quantity, so it's a quantity defined from the spectral properties of the process x. And the convergence happens uniformly in x. That's hard to obtain. At the velocity, essentially 1 over 1 plus 2. Okay. And of course, if we have this property and this property, we can divide. We can consider. We can condition by the survival event nt strictly positive, that give us an additional t plus 1 and an additional b. Okay, since here we had b n minus 1 and t plus 1 n minus 1. Okay, and what we obtain is that the expectation of the moment of ZTF over t plus 1 times this constant ab to the n, condition on survival at time t, will converge when n tends to infinity through n factorial mu f to the n. And we can observe, because we have to think about at the level, the measure level, that n factorial is is the moment of order n of an exponential random variable with the mean 1. Okay, that's a remark. Okay. So I just give you ideas of the proof of this property. So we have first to prove that mu 0 of tx. So remember, it's the survival probability at time t for the process issued from an individual with state x. Okay. And we prove that the survival probability tends to 0 when t tends to infinity uniformly in x. Okay, so we have extension when we are in this critical situation, but the convergence is uniform in x. Okay, so to do that, since u0 is of course is x fixed, it's decreasing in t by definition, we can consider the limit h of x. And so we want to obtain an equation for h to prove that h is equal to 0. And to do that, so we have seen that here the equation on u involves the first order moment of zt1, and we are not able to control this term. So we need another recursion equation. And to do that, we introduce, we consider another semigroup, where here you don't have anymore the growth rate, v minus v, which is b minus d, but we consider minus the jump rate, b plus d. Okay, that means that that corresponds to conditioning by the first jump. Okay, the first jump as a rate which is given by the jump rate b plus d of x. Okay. And so we can write another recursive equation for u0, which now involves this exponential with w here, which is minus b plus d instead of this. But we have here we have here qt1, and qt1, you see here you have minus b plus d, so it's easy to prove that this quantity tends to 0 when t tends to infinity. Okay. And then finally we obtain an equation for h, and using the assumption h2 and h3, we can prove that h is equal to 0. So in all this framework, as you see, we very often conditioned by the first jump and see what happens. Okay. And now also that technique, it is due to Pierre Collet, which is called the trapping set techniques. So we decompose u0 of tx on its projection on theta 0 plus the orthogonal projection, 5. And so we have two terms r of t theta 0 of x and psi of tx. And these two terms are solution of two equations, which are written here. And so I will not develop all the techniques, but what we prove is first we prove that r of t times 1 plus t converges to 1 over b. It's big velocity here. And we prove that psi of t is less in uniformly in x is less than a certain constant r square of t. So we do that, and finally we obtain the properties that are this paper. Okay. So now, as we have seen, we have this property, and now I can replace here f by any function of the form alpha j plus beta, for example. And then if I do that, I will obtain some information on the conditional joint distribution of ztj and t, which is zt1. Okay? Because I can consider all the function alpha j plus beta and with any alpha and beta real numbers. And that gives me the asymptotic behavior of the conditional joint distribution of this quantity. And in particular, so we have the convergence of all the moments. And so we can prove that we have the convergence of any functional of this quantity. Okay? So here zt is a measure of the process, but we consider a function of this quantity zt integrating j over this quantity, and the same for nt, and condition to the survival. And we can prove by our results that this quantity converges when t tends to infinity, and that we are at the level it's a result of convergence for the measure value process here, since we have the good test function, and that converges to the expectation of f of nu j, nu is the quasi-stationary distribution I introduced at the beginning of the talk, times the exponential random variable within one we observed previously. Okay. And in particular, if we forget the second coordinate, we obtain the Jaglom limit for the process Z. Okay. We prove that the random measure zt over t plus 1 ab, conditioned on non-extinction at time t, converge in law to the measure lambda, which is so psi is the exponential with rate 1. So lambda is a measure on the finite measure set. Okay, and defined like that, you have exponential of minus z times Dirac measure on Z nu. Nu is given, that's a stationary measure of d mu dz. Okay. That's the diagonal limit at the measure valued processes level. Okay. And since we have the John distribution, we have also convergence of the ratio zt of f over nt, condition on survival, and that will converge to the Dirac mass at nu f now. And we have also a sort of central limit theorem, but which is not central at all, because we consider ZTF over t plus 1 minus nu f AB. That's what we were waiting for, but we divide by 2 here. We have a certain constant in front of this difference, and we renormalize here by the total mass nt over t plus 1. And that condition on survival at time t that will converge to this law. So remember, psi is the exponential random variable with mean 1. And this, so the theorem, the first theorem, gives us this convergence. But here we have to, you see that we don't renormalize by zt, but we renormalize by the total mass. And so it can be different to consider the total mass or ZTF. We can, and that this difference is weighted by this 1/2. We cannot explain more than that, but okay. And so I wanted to show you an example, which was the first, the motivation of the paper. So that in the paper we did with Vincent Calvez, Benoît Henry, and Tran, and which was based, which was so the motivation was the modeling of adaptation for a population, the adaptation to a gradual environment, which evolves at a velocity c. And to observe this adaptation, we were with our modeling, we were consider birth and death diffusion process as before, with v of x given by this quantity 1 minus x squared over 2 minus a certain alpha, and we will consider the case where alpha, we will see the value later, is such that the problem is critical, the process is critical. And the diffusion is just a drifted Brownian motion. So the Brownian motion describes the small mutation you have all the time, and this drifter is due to the gradual environmental change. Okay. And so in this case, we can make all the computation really with the hand, and with using this transformation, PT is related to the semigroup RT, and RT is a semigroup on the Brownian motion, which is related to this spectral problem. Psi k and mu k are the eigenvalue and the eigenfunction and the eigenvalues for this spectral problem associated to this semigroup. And this one we know because we know that we have exactly the form of the psi k in this case. They are given in function of the Hermite polynomial of the density. Okay. And we also know what are the eigenvalues. They are given by this expression. And we know exactly what is the first eigenfunction psi of 0. And so we can make all the computation with the hands. And we deduce that the first eigenvalue minus lambda 0 is 1 minus alpha minus c squared. The c is the term in the front of the drifter, plus sigma, the diffusion coefficient over 2. And so for alpha equal to this quantity, we are in the critical case. Lambda 0 is equal to 0. And so we can obtain all the computation, and we can compute theta 0, mu 0, and then we have the value of the constant A and B. And we know that here the stationary measure mu is a normal law centered in minus C with a value sigma. And we have exactly the convergence of the measure ZT over T plus 1 AB with these values to condition on non-extinction, of course, to the diagonal limit lambda. Okay, so that's an example we had in mind. And just I would like to finish to say that the Feynman Kac semigroup are interesting because they relate the underlying Markov process to the linear projection of the measure valued process. But it's more than that because, in fact, you have a trajectorial version of this result, meaning that instead of considering ZT, which is the sum of the Dirac mass of the individual straight at time t, you consider all the trajectory until time t. Okay, so that's easy to define. That means the trajectory of an individual at time t, you will add all the trajectories related to its ancestor until time 0. Okay, and so that's it's called the name is a historical process. Okay, it was introduced by Bertin a long time ago. And so here you have a measure value process, but on the space of measure on trajectories, stopped at t. Okay? And so what we have is a functional version of the Feynman Kac property. That means now if we consider a function phi, functional defined from the set of continuous functions into R. And so we consider the expectation of HT phi, that means the sum of over all individual alive at time t of phi of the trajectory which describe all the histories, the lineage of an individual with trait t. Okay, for example, all the genetic history of the individual until time t. Listed here. And then we have also this decomposition using the Feynman Kac semigroup. Okay. And here, so it's exactly, you have always this exponential weight involving the growth rate times now phi of the trajectory x t, which is x stop at time capital T. Okay. And so what we can prove using this is that we have a Q process. That means that if you consider the trajectory of the process until a fixed time s, okay, and you condition to the survival until time capital T. Okay, s is less than capital T, and you make capital T tends to infinity. Okay. Then what we can prove is that this is asymptotically this quantity. Capital S is a function, is a bounded function, is a test function here. And we can prove that the limit is given by this quantity. That means that at this infinite dimensional level, we find an expression for involving the law of the process, historical process HS, but here we have a renormalization. It's a sort of H transform was given by this. And theta 0 is already the same. Okay, thank you.
Thank you very much, Sylvie. So are there any questions?
Yeah. Why in the critical case you can have a limit or concentration distribution? Because for the branching, when you are in the critical case, you have not.
Yes, but here I think that the diffusion plays a
Yeah,
role.
that is where is the that is a very important property, no? How you can, where is in your equation Well, how you can,
I think that
why
we have all,
probabilistically is it?
but we have all these spectral properties on the diffusion that
Yeah.
you don't have if you say constant. I mean, so that gives some. Where is the miracle? Yes.
No, but it's not probability because exactly that critical case you will not have a very, very interesting.
Can you put the diagonal limit thing, the equation that that is mentioned,
The what?
the diagonal limit thing?
No.
Thing.
Thing. It's not the standard diagonal limit.
Yeah.
No,
Yeah.
yeah. Red, you have normalized by T.
Yes, also.
So it's the diagonal limit of.
But even though when you
Yes,
normalize,
also.
by
No, but it's
by
we are only playing
not-
between the properties, as I said, between the properties of the growth rate and the properties of the diffusion.
Yeah, yeah,
And
yeah,
so that's the mixing
the
of
mix
both,
of the-
which
of both,
means that to know exactly perhaps
Because
perhaps
even
in
for-
5 years we will.
Even
And that the mass goes like.
But
even for critical,
no, but
even in branching when you
you're
divide,
right.
yeah, it is not.
But you really need the irreducibility of the process. That means you have to go in a lot of places.
Thank you.
And,
Maybe in the same direction, because so here what you get is some kind of exponential dilation of the quasi-stationary of the diffusion, but that means that you have support which is infinite in a way. So, I mean, because the measure is nu is the measure which was
mu, it's a measure on R.
but what
Mu
was
is
the
the initial measure. Essentially, it's related to mu zero. It's mu zero over its mass.
okay.
Mu zero is hidden left
Mhm.
hidden vector.
because in the subcritical case, just for the mass, you would obtain.
So in the subcritical mass, we have different regions.
But what would be good for? Because
Because at the beginning I wanted to subcritical case, so I show you. Okay, so that's here. Here we have directly an information on ZT, not ZT renormalized by one plus T. And so we have a certain probability, the limit is a certain probability which is characterized by the so-called hamburger problem. I didn't know the name. That means that you characterize the distribution by all the moments. Okay. So in statistical mechanics, it has another name, no? This no, it's hamburger problem. Okay. And okay, so it's a certain it converges to some measure, but I don't know.
Laplace problem.
Yeah, that's right.
It is the Laplace problem. When
Hamburger refers more.
to the Laplace.
Hamburger refers,
Right.
I think, to
Right.
the sufficient condition.
To have the Laplace, to be characterized by your class.
But in this case, you multiply by the zero. So the survival probability.
No, the good renormalization is exponential lambda 0 t in the subcritical
But
case.
there must be something.
And the limit has
And then it's okay, it's
There is something else.
I think it is something similar
Here you have what you are waiting
with
for.
before.
Yeah, but there must be.
Critical case, I don't know how it
Yeah,
happens.
but it was exactly
You have to explore the space
That thing was
sufficiently,
PT
but I
divided by
don't know exactly.
Yeah. It is.
But if here
Yeah,
it's not-
but you do not have when to condition you.
So I have a naive question. What happens if your diffusion has explodes in finite time? Like you are killed by.
I don't know. Not a soft killing, but a hard killing. I don't
you
know.
explode to infinity.
Yeah, or minus infinity because
The underlying diffusion, but yes, I don't know that. Then to define the measure valued process, I don't know, because on each branch you can explore. how do you define the process, the measurable value process?
Somehow when you type infinity,
Yes.
you are killed, you know.
Yeah.
You are just killed because somehow it's like evolutionary suicide or something.
You need a predator. The fear. No, well, I don't know.
Any other questions? So in there's many people on the Zoom. So if not, let's Sylvie again. Well, this is time you're here so we can offer some coffee and